B9, the Pythagorean Theorem. Now, this theorem deals with a right triangle. So one angle is 90, and we want to relate A, B, the two sides here, other than the hypotenuse, relate those to the hypotenuse. So the rule is, which we'll show, but let's give the rule first. C squared, the hypotenuse squared, is A squared plus B squared. So you square each of the sides, which are not hypotenuse, and add them together, and you get that. A lot of times we use this equation to find the hypotenuse by taking the square root of A squared plus B squared. Or sometimes we have C and A, but to find B, one of the others. Okay, so that's the formula. Many years ago, when I was in grade school, I saw this picture and was fascinated. There was 3, 4, and a 5, a 3, 4, 5 triangle. It makes a right angle, has a right angle in there. And by drawing these boxes, you could see that for the side that has 3 units of length, you have 9 boxes in the area, 4 by 3 by 3. With the 4, you have 4 by 4, you have 16. And the hypotenuse is 5, and you have 5 by 5, you have 25 squares. So, in other words, the 25 squares in here, if you add the 16 here and the 9 there, so you get 25. So, the hypotenuse squared is 5 squared, 25, and then this side, 4 squared, and that side 3 squared, and you get the result that C squared equals A squared plus B squared, which is a specific example here. But we would like to show this, well, we really didn't really prove this, so we would like to show this in general in a more rigorous way. This would have been done by like drawing the thing to scale with a ruler and marking things off. But we have a better way here, which I'm going to show you. It's in the text, which you can download. But I'm going to show you here with these pieces. Now, these pieces here, each of these are the same. So if you put them all together, you see, they're the same. And you have a right angle at 90 degrees, and then you have angle alpha and angle beta. I put A and B opposite their respective angles, Greek letter. The first Greek letter is alpha, first Latin letter is A, so they kind of go together, and then beta and B. C is paired with the 90 degree angle there, the right angle. Now we're going to need to know that alpha and beta are complementary. That means that when you add them together, you get 90. But first we might just review some basic geometry to show you that, review for you that the triangle has 180 degrees. So that's what I would like to show. Now, if you have this line that's parallel to this line, and we're going to look at a triangle, so that we draw in here like this, then I'm going to show you here this angle is the same as this angle. And see, this angle is the same as that angle. Now, even though this looks like a right angle, it's in general, so we can't say anything about this angle. We might just say it's a third angle, and I'll do these different arcs to emphasize different angles like we used to do in high school. Now, this alternate interior angle, which I like to think of as El Zova, the Zora rule, the Z, these are alternate interior angles. They're going to be the same. And if you want more of a review of geometry from high school, let's do it. Let's have another line parallel. So these are parallel lines, so that, say, this angle here, if we put this angle here as a 1, and if we go here 2, and say 3 and 4, and then 5, 6, 7, and 8, that here, all we need to use is that a straight line by definition is 180 degrees. So if that's the case, then the one angle and the second angle equals 180. But this is a straight line too, so that means 2 and 3 would be 180. Well, that means 1 has to equal 3. So this is a very, very basic thing that we can show, that if we have the two lines across, that this angle up here will be the same as that angle down there. Okay, now if you look at this parallel line with this one, and you have this slice like this, then 2 here would be equal to 6. Say 2 is equal to 6. These lines are parallel, right? So 2 and 6, it's basically a corresponding angle. It's like the same sort of, two lines, crossing, one horizontal, one with the same slant. So 2 and 6 are the same. But then here, the same logic would be 3 and 8 are the same. But if 3 and 8 are the same, and 2 and 6 are the same, we can look at, first of all, where is our Z, all right? This is our Z. I'm gonna make this our Z, because there's a lot of relationships here we don't need. So let's focus on this Z. So 2 and 6 are the same, but then we agreed that these opposite angles are the same. We already showed that. So that means 6 and 7 are the same. So that means 2 and 7 are the same, and that is our Z. It's a backward Z here, going like this, where these are the same. These are alternate interior angles. I sometimes say alternating interior angles. I got in the habit of doing that long ago. So by doing this Z, the alternate interior angles are the same. These are the same. And here's a backward Z. These are the same. So once when we do that, we can see that since the angle with the 1 arc plus the 2 arc and the 3 arcs equals 180, well, I have one of each in the triangle. If that's 1, see, second angle and 3, well, I have a 1 here and a 2 and a 3. So this demonstrates that in a triangle, you have 180 degrees when you add up the angles. I wanted to just take a little bit of time. This is a review chapter, this chapter B, and I thought it would be nice to just review a little bit of high school algebra, but this course that we're looking at here is going to get very advanced. Eventually, it's going to be graduate level work, as we're going to go slowly though. My style is to go very slow and show things and how they're related. So what this means is that alpha, let's look here, it's a little bit, contrast is better. That means alpha, beta, and the 90 has to be 180, which means that alpha and beta would be 90 when you add those together, because you have to have 180 in the triangle. So what I would like to do now is look at, say, this square here. I've cut this out. This is the fun proof. A proof by visualization. I love those kind of proofs there. That's very, very nice. So here what we're going to do is we're going to put together here these triangles like this. Go ahead and put that one there. And I cut this just right so that this would be matching right there, so that what I would have is this is side B. So this is B, and since this is B, this would be a square with B. But wait, how do we prove it's a square? Well, we got to be careful here. What we're going to do here is remember that we said alpha plus beta is 90. Well, here's alpha plus beta, so that's 90. So if that's 90, this is a straight line, this has to be 90. See? And that's 90 there, so that's 90. And over here, same thing, alpha plus beta is 90. This is going to be 90, that's a straight line. And if I have this work that with 90, 90, 90, then these lines, when they cross, they will be 90 also, because this is perfectly horizontal the way I set it up, and this would be perfectly vertical, so that's 90, which means this is a square, and the area is b squared. And likewise, the area here is a squared. So when these triangles take up space, what's remaining is the white, and that's that remaining white area is equal to a squared plus b squared. All right. So now what we do is we shift this over to here, slide that down, and shift this over. Now, this looks like a square with C, C, and C, but it really should demonstrate that this is 90 degrees. This is really a square, but let's do that. This is a straight line, that's 180, and you have alpha plus beta is 90, so what's left? This one. So this one has to be 90. Here, the same thing. This is a straight line, so you have alpha plus beta is 90. This has to be 90. Same thing there. So that means this square, this is a square, and it has side C, but that's the remaining white area. If the remaining white area now is also C squared, then we have shown what we wanted to prove, that for a triangle, and we just take one of these triangles out here and just isolate it. For the triangle, a squared plus b squared is c squared. Here I just labeled that one b, labeled that one a there. So it doesn't matter, it works. So isn't that cool? That's a nice theorem, and that dates back many, many years to Pythagoras, the Greek mathematician.